Let's look at example 5 now. Write polynomial functions using conjugates. This is the last example. Let's look at part A. What is a quadratic function p with rational coefficients in standard form such that p of x equals 0 has 2 plus 5i as a root? So do you remember the concept, the conjugate root theorem that we just looked at in the previous video? Yeah, so we know that there is a conjugate pair for conjugate roots, for the complex roots. So first of all, by the fundamental theorem of algebra, right, you know that quadratic equation has two complex roots. Since 2 plus 5i is one root, its complex conjugate, 2 minus 5i, must be the other. So what do you need to be able to write? What do you need to find to be able to write the equation with the given root, right? You just have one root, but by the conjugate theorem, then you know that you need to find the complex conjugate of this given root, which is not hard. You just change the sign of your second term, and then that's your conjugate. So use the factor theorem to write the equation quadratic function using the two roots, 2 plus 5i and 2 minus 5i. And then you're going to distribute, use associative property, group them, and then difference of squares. And then you simplify. Finally, you have x squared minus 4x plus 29. So that's the quadratic function p, where you have 2 plus 5i as a root. So you're going backwards. You're not just finding roots. If you're given one root, can you write a quadratic function? There's not only one answer for this type of question. Of course, you may have other polynomial equations that may have this root, but this is the most simplified one, because if you have these two, this root, this complex root, then you need to have another complex conjugate. And you can add any other roots like x plus 2. You can add a real root or whatever, and you can figure out other equations, but this is the most simple equation you can find where you have 2 plus 5i as a root. Okay, let's look at part B. A polynomial function q of degree 4 with rational coefficients has zeros, 3 minus root 7 and 4i. What is a polynomial equation in standard form with these roots? So what's another way to determine that the function q must have a degree of at least 4? So the problem says that q has rational coefficients, right? So because of the conjugate root theorems, there are 2 more zeros in addition to the 2 that are given. So the conjugate for 3 minus root 7 and the conjugate of 4i. Oh, look at 4i. Some students would be like, oh, what's the conjugate of 4i? I don't see any other terms. That's okay. You still have a conjugate. So yeah, it could be just 0 plus 4i, right? So that's already in a form of complex number. So you can just change the sign of this term, which is the second term, and then make it a negative 4i. Okay, so yeah, the zeros of q are the same as the roots of q of x equals 0. So since one root is irrational and the other is complex with non-zero, the conjugates should also be roots. So put all these 4 factors. This is the least number of factors you need to have. Otherwise, it doesn't make you'll come up with a different equation that doesn't really make sense. Okay, so distribute and then regroup because you want to solve for it, and then use difference of squares, simplify, and you have this polynomial with real coefficients: x to the 4th power minus 6x cubed plus 18x squared minus 96 x plus 32. And this polynomial has roots 3 minus root 7 and 4i, as well as their conjugates 3 plus root 7 and negative 4i. Okay, so it shouldn't be too hard. If you see complex number, any complex number, the conjugate should also be the root. They go as a pair. All right, let's look at try number 5, A and B. What is a quadratic equation in standard form with rational coefficients that has a root of 5 plus 4i? And part B, what is a polynomial function q of degree 4 with rational coefficients such that q of x equals 0 has roots 2 minus root 3 and 5i? So pause the video, see if you can figure it out by yourselves, and come back when you're ready for answers. Okay, are you ready? Yeah, so by the conjugate root theorem, we know that the conjugate of 5 minus 4i should also be your root. So for 5a, you need to figure out the two factors, x minus 5 plus 4i, and then x minus 5 minus 4i, okay? And then you're going to regroup them so that you have the same factor, x minus 5, and then 4i times x minus 5 again, minus 4i. And then you rewrite as difference of squares, x minus 5 squared. And then yeah, and then minus 4i squared. And then you square them. X squared minus 10x plus 25, and then minus 16. I squared is negative 1, so plus 16. And then you add 25 and 16 together, 41, right? So then your quadratic equation should be x squared minus 10x and then plus 41 is equal to 0. Easy. Okay, and then let's look at 5b. Polynomial function q with a degree 4, needs to be degree 4 with rational coefficients such that q of x equals 0 has roots this and that, so you just have to write the 4 different roots, and that's going to give it a degree of 4. So x minus 2 minus root 3, and then x minus the conjugate 2 plus root 3, and then times x minus 5i times x plus 5i. Wait. Yeah. And then you group them and use difference of squares. So that would be x minus 2 squared times minus what is it? Root 3 squared times x squared minus 5i squared. Okay, and then you square them. X squared minus 4x plus 4, And then you square it, it's going to be 3, so minus 3 times x squared minus 25, but then it becomes positive because of I squared. And then you multiply them again. And then you have x to the 4th power minus 4x cubed plus 26x squared minus 100x plus 25. Yeah, so q of x is equal to x to the 4th power minus 4x cubed plus 26x squared minus 100x plus 25, and that's equal to 0. Okay, good. Check your answers and see if you got it right. If you did, great job. And that was your last try it. Great job. Let's summarize our lesson. If you look at the concept summary in the next page, you'll see the theorems about roots of polynomial equations that we looked at in this lesson. So the rational root theorem it says that for any polynomial equation that looks like this, there is a limited number of possible rational roots, and it's related to your degree of the function. And the rational roots must have reduced form p over q, where p is the integer factor of the constant term and q is the integer factor of the leading coefficient. And then you can use substitution, synthetic division to check roots. So this is an example. And then we looked at the fundamental theorem of algebra, which basically says that there's exactly n solutions in a set of complex numbers. So whether real or imaginary, all the roots should equal to the degree of the function. And lastly, the conjugate root theorems, where you had irrational conjugates and complex conjugates, but you need to have the conjugates if we have any rational or complex numbers as roots. They come as a pair. All right, so that was our lesson 3-6, theorems about roots of polynomial equations. We'll continue with the last lesson in the next video. Bye.